Welcome to section 14.5 Similarity. Remember to do all the problems along with me. This section is a little bit longer because we've got lots and lots of examples. All right. Model cars, trains, planes, they are exactly like their real life counterparts. Maybe exactly was too far, but they're just smaller. So we can imagine scaling these things down. In geometry, we use the notion of congruence, as we just learned, as a precise way to discuss things that are identical. But this idea of similarity is a precise way to discuss shapes that are identical except for their size. So everything else is identical. Similarity is really important. We need it for understanding lines, equations, surveying, map making, representational drawings. So in this section, we're going to cover a lot of different examples about similarity. So first, informally. Informally, we could say two objects that have the same shape but not necessarily the same size are similar. And we've seen that before. If we've got this rectangle and this rectangle, we would say, hey, those are the same shape, but they're not the same size. We would call them similar. And that can actually be misleading. As you're going to see, that's an exploration. Another way to describe similarity informally is as follows. Two objects or shapes are similar if one object is a scaled version of the other. So a scale model of a train is similar to the actual train on the outside. Networks of streets on a street map are similar if the streets were on the flat ground. So one way to create a shape or design that is similar to another is by using grids. So if you have done any art or crafts, you may actually be familiar with this technique. So we're going to draw a grid of equally spaced parallel and perpendicular lines over the design that we want to scale. And then if we want the new design to be, say, twice as wide and twice as long, then we would make a new grid of parallel and perpendicular lines that are spaced twice as wide and twice as long, and then copy the design onto the grid. And this will be similar. So let's do some explorations before we begin. Complete this exploration. This one's really important to help us understand the difference between similarity, formally and informally. And then complete this one before we move on as well. Press play when you are ready. So let's go back to that craft project. Let's use this to help us define similarity more precisely. So the grid for the large bunny was made so that the width, thought that was on my highlighter, so that the width and the height of the large bunny would be twice the width and the height of the small bunny. But notice that all lengths on the large bunny are twice as long as they are on the small bunny, and that scaling is the key aspect. Here's the precise definition right here. Mathematically, we say two shapes or objects are similar if every point on one object corresponds to a point on the other object, and there is a positive number k such that the distance between any 2 points on the second object k is k times as long as the distance from the corresponding points on the first object. Holy smokes. Let's go to this bunny to look at it for a moment. This is the original bunny. These bunnies are not similar to these, and you can kind of just see that by looking at it, but that's because they're not scaled the same around, right? The middle bunny is tall but not as wide. The last bunny is wide but only half as tall. And when we talk about similarity here, this scale factor, this k number, it has to be consistent. It has to match on the same amount of width and height. So notice here that it's twice the width and the height, and that's how we end up with something similar. That twice means our k is 2. So let's think about this for a second. If the box of a toy model car might indicate that the toy car is 24:1 scale model of an actual car, this means that the toy car and the actual car are similar and the scale factor is 24. Or to look at it the other way, it'd be 1/24. And that can be tricky is when we look at the scale factor in one direction and the other direction, they're different because one makes it bigger and one makes it smaller. So if we think of the actual car is going to be 24 times the length of the width and the height, all of it. And the distances such as the width and the windshield, everything is going to be 24 times. Everything. And that's the key for similarity. Notice that it does not work for areas or volumes. It only works for one-dimensional lengths. So length, width, height, etc. Let's do an example to make sense of this. These two are similar. Okay, they tell us these are similar. Name the things that correspond. So the corresponding sides here. So look at your right angle to kind of ground you in, okay? So from the right angle out, okay, so we've got FG is similar. That's our symbol for similar. And then our right angle out is going to be IJ. And remember that it is important the way that we write it. So then we've got our right angle up, so that's going to be FE is related to right angle up IH, and sometimes you'll see these line segments over. And then EG is similar to, and make sure you go HJ. We want to make sure that the letters match with their corresponding part. So now angles, well, we can say angle F, and now these are going to be corresponding. So I'm actually, you know, I kind of jumped the gun here. Let's just say those two are related. So F and I are corresponding. F and I. G and J. And then E and H. And I'm not going to say similar because they're actually congruent, but we're going to find that out soon. Triangles A and B are similar triangles. Find the ratio of the corresponding sides of triangle A to triangle B. So they don't want us to actually find the values of anything here at first. Let's just find the ratio. So if we look at this, remember that everything has to be scaled equally. So we could say, okay, they want us A to B. So the order does matter, A to B. So that's the same as A over B if we think about our ratios. So A, this side length, 33, corresponds to 11. And this side length on A, 18, corresponds to 6. And this side length on A, 15, corresponds to 5. What do you notice? What's 33 over 11? That simplifies to 3 over 1. 18 divided by 6. 15 divided by 5. They should all be the same ratio, so the answer here is 3 over 1. That is the ratio of the corresponding sides. If K corresponds to N, name the proportional sides in these similar triangles. So if we kind of go back here, a ratio is the same thing as a fraction. This is old stuff, but I just want, we've got A over B. And a proportion is when we set two ratios equal to each other. A over B is equal to C over D. So they want proportional sides. So they want to know what matches up. So now if we were to take this guy and kind of think about flipping it over so that we could look at the point the same way. We know that the top of that point there is L. And then if we flipped it over, this point would come down and this would be M. And then, well, let's see here. It looks like, yeah, it looks like this one's a little bit longer, doesn't that? This is a really tricky one, and hopefully they're not all so tricky here, but that one looks like it would switch, it would come down, and then maybe it would even rotate, actually, instead of flipping. This might actually rotate so it lands at P. This longer side is M. And that's okay, honestly, if you couldn't tell, because these triangles are poorly drawn here. So now if we kind of have this here, what relates? Proportional sides. So O to N, what does that relate to? O to N is going to relate to L to K. And the order does matter, right? We didn't go NO. If we did NO, it would be KL, which is fine, but we just got to match it up. So now we've got O to P is going to relate to L to M. And P to N is going to relate to M to K. And now here's the thing. It's okay if we go the other way. It's just we have to match it up. So these are the proportional sides in these similar triangles. And when we come back, we're going to actually look at how to determine those ratios and the two different methods we use.